Right now, as you watch this video, a signal is traveling beneath the ocean floor. That signal is not wireless. It is not satellite. It is light, trapped inside a glass fiber thinner than a human hair. 95% of all international internet traffic crosses the world through submarine fiber optic cables. These submarine cables sit at depths of up to 8 kilometers below the ocean surface. There are over 500 active submarine cable systems crisscrossing the ocean floor today. Together, these submarine fiber cables span more than 1.3 million kilometers in total length. That is enough fiber optic cable to wrap around planet Earth more than 32 times. Today, we are going to cut this submarine cable open and see exactly how it works. The story of submarine cables begins in 1858, long before the internet even existed. The first transatlantic telegraph cable connected Ireland to Newfoundland across the Atlantic Ocean. That first telegraph cable failed after just 3 weeks, but the idea was revolutionary. By the 1950s, coaxial telephone cables were laid across the ocean floor for voice calls. Then in 1988, the first transatlantic fiber optic submarine cable changed everything forever. Fiber optic submarine cables could carry millions of times more data than copper telegraph cables. Today, a single modern submarine fiber optic cable can carry over 400 terabits per second. That is enough bandwidth to stream every movie ever made, simultaneously, in 4K resolution. Let us now perform a complete teardown of a submarine fiber optic cable, layer by layer. From the outside, a submarine cable in deep water looks like a simple black board about 25 millimeters thick. But inside this submarine cable is an extraordinary layered engineering system. Layer 1. The outermost layer is a polyethylene jacket, a tough plastic sleeve protecting everything inside. This polyethylene outer jacket must withstand crushing deep-sea pressure up to 800 atmospheres. Layer 2. Beneath the polyethylene jacket lies a layer of steel wire armoring, twisted in a helix. These steel armor wires protect the submarine cable from anchor damage and fishing trawler nets. Layer 3. Inside the steel armor is a second polyethylene insulation layer for waterproofing. Layer 4. A critical copper power conductor runs through the center of the submarine cable. This copper power conductor carries between 5,000 and 10,000 volts of electricity along the entire cable route. That high-voltage electricity powers the signal repeaters buried along the submarine cable route every 70 kilometers. Layer 5. Surrounding the copper power conductor is an aluminum water barrier to prevent any moisture penetration. Layer 6. Inside the aluminum barrier is a polycarbonate hard plastic casing for structural rigidity. Layer 7. At the very center of the submarine cable sits the fiber optic bundle, the heart of the entire system. Inside the fiber optic bundle, there are typically between 4 and 24 individual fiber optic strands. Each individual fiber optic strand is only 125 micrometers in diameter, thinner than a human hair. So how does a fiber optic strand actually transmit data at the speed of light? The answer lies in a physics phenomenon called total internal reflection. Each fiber optic strand has 2 layers, a core glass and a cladding glass with different refractive indexes. The core glass has a slightly higher refractive index than the cladding glass surrounding it. When a laser beam enters the fiber optic core at the correct angle, something extraordinary happens. The laser light bounces, it reflects off the cladding and stays perfectly trapped inside the fiber optic core. The light bounces back and forth inside the fiber optic core, traveling forward along the entire cable route. This total internal reflection allows light to travel through thousands of kilometers of fiber optic cable with almost no signal loss. But the light carrying the data signal is not ordinary white light. It is a precisely tuned laser beam. Modern submarine fiber optic cables use a technique called wavelength division multiplexing, or WDM. Wavelength division multiplexing means multiple laser beams of different wavelengths, different colors, travel through the same fiber optic strand simultaneously. Think of it like a highway with many lanes. Each laser wavelength is its own dedicated data lane inside the fiber optic strand. A single fiber optic strand can carry over 100 separate wavelength channels simultaneously using advanced WDM technology. Each wavelength channel inside the fiber optic strand can carry terabits of data per second. Now, light does weaken over distance. Even in a perfectly engineered fiber optic strand, signal attenuation occurs. This is why submarine cables need repeaters, specialized amplifier devices placed along the cable route every 70 to 100 kilometers. Each submarine cable repeater contains an erbium-doped fiber amplifier, known as an EDFA, that boosts the optical signal without converting it to electricity. These EDFA repeaters are sealed inside titanium housings designed to survive decades of deep-sea crushing pressure. Building and installing a submarine fiber optic cable system is one of the most complex engineering feats in the world. It requires specialized cable-laying ships, massive vessels over 100 meters long, equipped with enormous cable tanks below deck. Each cable-laying ship can carry up to 10,000 kilometers of fiber optic submarine cable coil inside its massive cable tanks. The fiber optic submarine cable unspools from the cable tank and feeds through a cable engine on the ship's stern. The cable slides down a curved guide chute, called a cable chute or linear cable engine, into the ocean water. In shallow coastal waters, the submarine cable is buried under the seabed using a remotely operated underwater plow vehicle. In deep ocean water beyond 1,500 meters, the submarine cable simply rests on the ocean floor under its own weight. Survey ships map the ocean floor months in advance to find the flattest, safest route for the submarine cable. Engineers must avoid underwater volcanoes, seismic fault lines, and military-sensitive zones when routing a submarine cable. A single trans-Pacific submarine cable project costs between $300 million and $1 billion to complete. Installation of a transocean submarine cable takes between 12 and 18 months of continuous ship operations. Once installed, a submarine fiber optic cable system is designed to operate reliably for 25 years or more. But submarine fiber optic cables are not invincible. They break. And when a submarine cable breaks, the consequences are enormous. The most common cause of submarine cable damage is human activity. Anchor drops and trawling fishing nets account for over 60% of all cable faults. Natural hazards including underwater earthquakes, turbidity currents, and deep-sea landslides also regularly damage submarine cables. When a submarine fiber optic cable fault is detected, engineers use a technique called optical time domain reflectometry to locate the exact break point. Optical time domain reflectometry works by sending a laser pulse into the fiber optic and measuring how long it takes to bounce back from the fault. A cable repair ship is then dispatched to the fault location, sometimes sailing thousands of kilometers across the open ocean. At the fault location, the cable repair ship uses a remotely operated vehicle, or ROV, to dive and retrieve the broken submarine cable from the seabed. The two broken ends of the submarine fiber optic cable are pulled to the surface and spliced back together on board the repair ship. Repairing a single submarine cable fault takes an average of 2 to 4 weeks from fault detection to full restoration. There are only around 60 specialized cable repair ships operating worldwide, yet they maintain the entire global internet infrastructure. The biggest tech companies on Earth, Google, Meta, Microsoft, Amazon, now own and operate their own private submarine cable networks. Google alone has invested in over 20 submarine cable systems across the Pacific, Atlantic, and Indian Oceans. These private submarine cable investments give tech giants direct control over international bandwidth pricing and data routing. Submarine fiber optic cables also carry real-time global financial transactions worth trillions of dollars every single day. A submarine cable cut near a financial hub can delay stock market trades by milliseconds, which in high-frequency trading means millions of dollars lost. Submarine cables are therefore considered critical national infrastructure by governments around the world. Military and intelligence agencies actively monitor submarine cable routes for signs of unauthorized access or tampering. In 2022, submarine cables connecting the Tonga Islands were severed by a volcanic eruption, cutting the island nation off from the internet for weeks. The next generation of submarine cables is being designed to carry petabit-class bandwidth, 1,000 terabits per second. New submarine cable designs are also integrating deep-sea sensor arrays to monitor ocean temperatures, seismic activity, and sea level changes in real time. Space-based satellite internet systems like Starlink are growing, but submarine fiber optic cables still offer 100 times lower latency and 1,000 times more bandwidth capacity. The humble submarine fiber optic cable, thinner than your finger, sleeping silently on the ocean floor, is the true backbone of our entire modern civilization. Every video you watch, every message you send, every financial transaction you make, all of it travels through this invisible underwater fiber optic highway. If you found this deep dive into submarine fiber optic cables fascinating, hit that subscribe button right now. New engineering breakdowns and technology deep dives drop every week on this channel. And leave a comment below, which technology would you like us to tear down and explain next?